This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Welcome to Science on Saturday. I'm Joanna Albala. I'm the manager of the Science Education Program at Lawrence Livermore National Laboratory, and I'm happy to see all of you here for our presentation this morning. So Science on Saturday is brought to you in partnership between the laboratory and the Livermore Valley Unified School District, and today we are lucky enough to have a board member, Chuck Rogie, here to introduce our presenters to you today. Chuck?
Good morning. Welcome to the third presentation of Science on Saturday. Last week's topic was producing green energy with light and wind. I hope you all were able to make that. Our topic today is back underground, though, the hydrology of an ant farm. When a farmer drills for water, where does that water come from and why? Today's speakers will give us an insight on how groundwater interacts with our environment and may affect our ecosystem and our daily lives. Dr. Andrew Thompson, along with science educator Aaron McKay, will discuss how the climate changes and pollution interacts with the water under our feet. Dr. Thompson is a hydrologist in the Atmospheric, Earth, and Energy Division at Lawrence Livermore National Laboratory. His research interests include physics of fluid flow, chemical transport, chemical transformation in porous media, fluid mechanics, groundwater supply and contamination, and the mathematical modeling of all these processes. Some of Dr. Thompson's published papers include analysis of subsurface contaminant migration and remediation using high-performance computing, and impacts of physical and chemical heterogeneity. Sorry, I'm just going to move on because I'm not going to say it right. On co-contaminant transport in a sandy, porous medium. Aaron McKay teaches biology at Tracy High School, where she takes part in extra activities like the Wakesman Student Scholars Program, biotechnology, and the Science Olympiad. Aaron has participated in many of the past Science on Saturday presentations and helped organize and instruct the Student Scholar Program at Lawrence Livermore Lab's Teacher Research Academy. So please welcome Andy and Aaron.
Got to have a little water before we get going. Thanks.
Thank you.
Okay. Thanks for coming out. And today's talk will be about water and groundwater. So I want to talk a little bit about, in general, where does our water come from in California? Where does it go? And what is groundwater? How does it all fit into this? Perhaps a lot of you have heard about that from the news and the drought we're having and that sort of thing. And so I want to sort of discuss how important it is to our water supply and how we can protect it in the future. So the way I want to try to do this is to use this physical model you can see over here, and we're going to go to that a couple of times and look at how things work in it. And it's not really an ant farm. There's no ants or anything. It's just kind of a little toy name I like to use to make you think about what it might look like, and it's a sort of a cross-section of the Earth, and we'll talk about that in a second. So when we think about where our water comes from, our minds go, well, it rains. Our water comes from the rain and the snow, and we live in California, and that's true. It's part of the hydrologic cycle, and that's where water evaporates off the ocean, it goes up into the sky and forms clouds and large bodies of vapor up in the sky, and in good years it blows over California and it rains and snows, and bad years it goes north, it does nothing here. But that's in general how it works, and then it rains or precipitates out, and then people will use the water, it goes under the ground, it runs off in streams, it will go underground as well, sometimes it will go off into the ocean, and then it may re-evaporate. So that's the hydrologic cycle. It's worth noting that there's some places in the world that get their water from outside the hydrologic cycle. Saudi Arabia and the Middle East, Kuwait, the Gulf states, they rely totally on desalination of ocean water. And here they're actually sucking the ocean water out and they're purifying it and drinking that. That's not part of the hydrologic cycle. There's other places in the world where I think I've got it called fossil water. They mine the water. So it's water it's there from a previous climate and they're mining it out, and when it's gone, it's gone. And I'll show you an example of that. And then there are also places where we actually, instead of discharging the water or wastewater back to the ocean, we actually treat it and recycle it and reuse it. And sometimes we invent a new cycle doing this. So going back to California, all of our water, all the precipitation that gives our water, most of it just falls in the state proper, and you say, well, that makes sense, but a lot of places that's not the case. So 95% of the water in California that is used actually falls in precipitation, and the other 5% is what we call imported water, and you say, well, what does that mean? And a lot of water in Southern California comes from the Colorado River, and that's water that falls as precipitation up in the Colorado River watershed in Colorado and flows in. So in California, there's a picture here of the annual average precipitation over the last 30 years, and what you can see is most of the precipitation falls up north in the blue areas, and very little falls in the southwest part of the state in the deserts area, and that, I think we all understand that. So it also always, it primarily falls in the winter. So in the summer, it's pretty much dry everywhere, and it's always dry in the south, and the only time we have a lot of wetness is most of it's up north, really in the winter. So if you can think of the water equation in terms of the inputs get moved into storage, or they get turned into outputs. It's a sort of a basic, it's like your bank account. You make money, you earn money, you put it in a savings account, or you pay off your expenses. And so if you lose your job or you're not getting as much money, you have a drought, then you're going to be living off of your expenses are always the same, so you got to live off of storage. So we're going through these cycles with water in California right now. So most of the water in California that falls, 2/3 of it goes away right away as evaporation. Or as I think the word here is evapotranspiration. Transpiration is when the plant root zones pull the water in and it goes off into the atmosphere. This is in forests and trees, all plants, grass. It's a very significant process, and in fact, 2/3 of the water that falls as precipitation disappears just back into the atmosphere. So the remaining 1/3 is divvied up into what you might often hear about is agriculture takes 80% of the water, and the cities only take 20% of the water. Well, that's true of this piece of the pie, okay? And there's another piece, which is actually what they call environmental water. And by law, a number of rivers have to discharge water to maintain fisheries. Or we like to maintain water flows in the delta. You hear a lot of discussion there about preserving the fish and the ecology in the delta because they need water for that. And if they use water for that, they may not be able to use it for ag and city supplies. But by law, there's a lot of this. And also there's, a remainder. In some years, there's a lot of excess. Some years not. And a lot of that is either goes into extra storage, and that's in groundwater, for example, or it's a discharge to the ocean unused. Okay, so there's a lot of, when water falls in the state, it can go into storage, or we often move it around in the state. And one of the big primary modes of storage is in groundwater basins. Here's a picture of California. You can see here all the orange and yellow areas are areas where there's large groundwater basins, and there's a lot of production of water. Most of it's in the darker orange. In the desert areas, there's still groundwater there. It's deeper, and there's not as much, but there is groundwater there as well. It's moved around. There's other modes of storage as well. What I want to say is there's snowpack is another important storage. When it's a large volume of water that sits up in the mountains until April, when it starts to melt and come down and fill reservoirs up. And reservoirs, of course, are another mode of storage, but they're only finite in their volume. And of course, there are lakes and groundwater, again, it's another artificial kind of groundwater. Now, we move water around in the state. Naturally, it's going to run off in rivers, runs through the delta. And, we've built a lot of artificial aqueducts and canals to move water around as well. But I'll go through this picture here. Here's a picture, of the snowpack in 2013. That's right. And that's what it looks like. You've been up there skiing and snowing, or when it's snowing and that sort of thing. Again, it's a very important part of the state's water supply. The amount of snowpack on average is equivalent to what all the cities use on an average year. So it's a really important part of the supply. But it's threatened. What it looks like a year later. This was a year later, 2014, same point in time in January. Hardly any there at all. And I would hesitate to say that the picture today would be about the same. And so we don't have that input to us. So we have nothing to store, nothing to use. And the question is this just a part of a natural drought cycle, or is it something telling us of what's coming in the future with climate change? And the big issue with climate change and snowpack is it's generally accepted to be warmer. And so the warmer it is, the less snow falls, and the more it falls is rain. So there will be less snow in the future with warming climate. So that's something we have to keep thinking about. In terms of moving water around, this is a picture of the state. Again, the boxes most of the boxes in this picture represent some type of reservoir managed by some type of agency. It could be Folsom Lake, it could be Shasta Lake, it could be Hetch Hetchy Reservoir. A lot of different agencies maintain reservoirs that capture pretty much snow melt. And then, and you can see most of these facilities are up north. And there's also a lot of aqueducts that move water around. There's the LA Aqueduct, there's the State Water Projects, there's the Hetch Hetchy Aqueduct. So there's a lot of different conduits, and most of those are going down south and feeding the needs in the south. So these are all man-made bits to help move water around and keep water in the state. And we need to understand how those work a little bit. But this is a close-up of the California Delta. Now, the Delta is sort of the natural heart of the water supply in California. And it's, by and large, it's mostly a natural layout of canals and rivers that collect water that comes from the north, from the east, and from the south, and normally would all discharge into the San Francisco Bay. Now, since we have reservoirs way up north and way east, like Shasta Dam, and they're collecting water, how do they send water from Lake Shasta, to Southern California? As they release it into the Sacramento River, and it flows into the Delta, and then they move it into what they call a forebay unit, which is at the bottom of this picture in the yellow box. And then they move it into aqueducts. And so there's a close-up of the forebay there. And you can see two aqueducts in which the water is pumped up to a higher elevation, and it flows by gravity down to the valley. And when you get down to the end of the grapevine, you'll see it actually being pumped over further, some of it. And actually, you can also see there's a branch of this that sends water to Livermore and to Santa Clara. And in normal years, if you live in Livermore, a lot of your water, you say it's Delta water, and it's Delta water because this is how it gets here. And given this year we're in a drought, we're not getting a lot of the allocation from this source of water, and we're in fact relying a lot on groundwater in the city. So I'm going to come back to that in a little bit. Again, reemphasize that groundwater is a critical resource. It occupies the pores of underground rocks and geologic materials. It's ubiquitous. It's found all over the place. You saw the map. It can be found at great depths, down to thousands of feet in some places. Typically, the amount of groundwater storage far exceeds the amount of reservoir storage in the state. And typically we produce it from pumping wells, and we're going to show you how those things work here. So we have a physical model over here where Aaron is standing, and I'm going to go through some slides here to show you what it looks like and to identify particular features, and then I'm going to walk over there and Aaron's going to do some demos and show it how it works real time, a couple of different times. So really it's a cross section out of the earth, okay? And this is sort of what it looks like if you're just looking at it from the other side of the air, from Aaron. You'll see this picture of a live feed here in a minute when we start running some water through the thing. It has a lot of different features, so I'm going to talk about the constituents. There's sand in this thing, that's like a geologic material. There's gravel at different layers. There's also an important layer of clay here, okay? And we identify these things with regard to their properties for water flowing through them, okay? So the sand area we call a shallow sand aquifer, and the word aquifer is used to refer to a formation whose water can be transmitted through it very readily. You can pump water out. It's like sucking water out of a glass of water. Whereas a clay is a confining layer, and water does not want to move through clay at all. It's like, you got the thickest milkshake. You can't get it to even come through a straw. So clay is kind of a barrier to water movement, and the sand and gravel are more transmissive units that water can be pumped out of very readily. In this case, we also have a feature on the top, like a landfill, and we'll use that a little bit later to show you what happens when somebody dumps something in there at midnight and nobody's paying attention to them, because it has effects downstream in the lake, potentially. We have a body there that looks like a lake. It could also look like a river. We could drain it from the back, but right now it's looking like a lake, and we'll look a little bit more at that. We have different kinds of wells. We have these small tubes inside this system, and they're meant to be or operate as wells. So we can pump water out of these wells. We can even pump water in if we wanted to. We have wells in the shallow aquifer. We have wells in the deep aquifer. And the deep aquifer has the word artesian, and I'll talk to you about what that means in a second. Actually, I'll talk to you right about now. There's a third well, which you can't see, which is hidden behind the dotted line here, and it opens up at the top, and what we have is a pipette tip stuck into the hole. And really, this is on dry ground, if you will, above the lake rim, okay? And what actually happens is you can actually get water to flow out of that well, if it's a man-made well, or if it's a natural feature or fracture, will flow out of it on its own pressure. We don't have to pump it out. And that means it's a flowing well. And that word artesian well really means a well that flows under its own pressure. And it's named after an area in France where this was used quite a lot, and they had these kind of conditions. So we'll talk a little bit about what we mean by the occurrence of groundwater. So this is a zoom in on the right-hand side over where Aaron is standing. And it's very hard to see in the sand where the water is. So if you look at the wells, you can see the water will rise up into the well up to a certain area. Like if I had the straw in my glass, I know that the water level in the straw is the same as the water level in the glass around it, okay? So it's the same trick here. There's gonna be water levels in these wells, okay? And right where that white dotted line is. And what that means is that below that level, all the pores are filled with water. And above that level, the pores have air in them and some water, okay, but they're not completely saturated. So hydrologists will call the area above the unsaturated zone, and they will call the area below the saturated zone. And the area, the surface that separates them is called the water table. So if the water table is high, there's a lot of water below it. If the water table is low, there's a lot of dry rock or partially saturated rock. In this particular case, the water table intersects the lake, so the lake level can be thought of as an extension of the water table. And this is very much, if you've been out to Shadow Cliffs Park, that's exactly what you're seeing. The lake level at Shadow Cliffs is commensurate with the groundwater level, because Shadow Cliffs Park, or the lake, was actually built out of a gravel pit that was extracted out. Okay, so the shallow, okay, so water can actually exchange between the saturated zone and the groundwater system and the lake. Water can go back and forth. That's useful to know. Unless, of course, the water level is really low. Now, you imagine yourself out in a desert, and you have a canal going through the desert, and you say, well, I'll show you that in a little bit later. If the canal is unlined, if it's like a ditch, water in the canal will infiltrate and will percolate down to the water table. And in this case, you can have exchange, but the water and the groundwater cannot go back up. So here we can lose water out of the canal to the water table, okay? We'll talk a little bit about how water comes and goes, the inputs and outputs to this system. Normally, there's rainfall, and we talked about evapotranspiration. So the first thing that happens, it might rain, and the water will accumulate on the ground or into the roots or into the unsaturated zone. It's going to evaporate back up or transpire back up. That's where most of it goes. But there's going to be a remaining bit that actually makes its way down and actually crosses the water table, and it adds water to the storage in the groundwater basin, and that process is called recharge. So there's a recharge of the aquifer. That's how water is, the hydrologic cycle ends up back in groundwater. It's recharged in this way. There are other ways water can come and go into the system. As I said before, it can exchange to and from the lake. In this particular model, we have a reservoir on the left and the right because it's not an infinitely wide model. So you can think of the left side as being, say, up in high hills or where the water tables are higher, and the right side can be down in a valley where there may be another river or something where they maintain the water level at the drainage point. Okay, so there's high water on the left, low water on the right. We can also pull water to this artesian spring, which I told you about. Can actually take water out of the system by a natural process. We can pump water out of the system, and doing so, if we pump more water than goes in, the water levels are going to go down. It's just like drinking water out of a glass, you know. And actually, in some cases, you might even put water into the system. You know, sometimes people recycle water. We've talked about that, and they can recycle it and use the groundwater aquifer as a reservoir. They can put it back in. That doesn't happen often, but it's a newer thing that people are doing these days. So, as I said before, you know, we have high water on the left, low water on the right, and it tends to want to drive a flow through the system. I have a little hose here, okay, and in the hose I have water level over here, and I have a water level over here. And typically, what you see is they want to be at the same level, okay? There's equilibrium, and if I raise this side's going to equilibrate very quickly, okay? And what happens in a real system is it doesn't equilibrate that fast. Water will flow through that system, but very slowly, like 10 meters a year. Now imagine.
Hold on. We don't want to get water everywhere. Safety
She thinks
first.
I'm going to get water. Imagine this being the ground surface and this being high, and I've got the water up here. So now there's a pressure here, okay? There's a pressure here, and if this is the ground surface for my thumb, I can let the water will come out all by itself under its own pressure. Now you can see the reason water is coming out of here because there's a weight of water over here driving it over. So when you see an artesian well or a spring, it's working the exact same way, okay? We're going to do this in a real model. Well, what if I were to connect all the shallow wells, the water levels? I'm going to get the water table here. And what if, and that's the kind of flow you're going to get through the system, okay? Now, I can also go through and connect and look at the water levels in the deep wells. Now, notice they're different. And in fact, what's going to happen is that's going to drive water out the artesian well because it can't go anywhere else. It wants to rise up to the same level as it started. And that level happens to be above ground. I think the first thing we wanted to do here was pump some water out of the system, okay? Now,
Which well shall we use?
well, let's see here. I think we want to use the pumping well. This is a big one for like a city well. It's got
Is that why it's got that big square thing?
Yeah, it's a big opening where water comes in at many different elevations. Now you might see there's some tracer here that she put in here. We'll talk a little bit about that later, but that might influence what happens in this pumping well. Go ahead and pump that one.
Let's see. Oh my, it takes a lot of energy to pull this water out.
Now do you see the water levels going down at all?
Did they go down?
I don't know. I mean, the water level in the well is right about here. Well, why don't you pump, do that again. I'll see the water level here. Maybe you might be able to see water levels going down.
And
The
pulling.
water level is going down over here while she's pumping up. It's also starting to get red.
Uh-oh.
So what you're seeing here is they're actually influencing how the water is flowing through the system. And hold on one second. The idea here in this red here, she put it in here originally as a way to show you how the water moves. So when she started, it was over here, and naturally it's wanting to move across the system, as I explained, because the water's high and the water's low, okay? So she's pumping the water out. Let's pump this one.
This is also a shallow well, isn't it?
But let's keep an eye on the water level in the city well.
Okay. They're both shallow, just a little bit different.
And so what you can see is the water level in the city well. The city well is now dry because she's pumping. So imagine, I operate the wells for the city, everything's fine, and she's just got this winery going. She's pumping all the groundwater out, and our city water supply has now been eliminated because of all this water. So water wells can influence one another and how they're operated, and they have this sort of drawdown effect. Now let's go down and pump the deep well, okay? She's built a new well, and it's deeper, and the idea is she doesn't want to affect the city, and it probably will not affect.
Is that because it's isolated by the confining layer?
Yes, it's below the clay layer. So the effects on the city well are not too significant because she's pumping out of a deeper area that's hydraulically separated, okay? Okay, and I think that's it. Now I think what we want to do is she's going to go along and connect, like we had the purple line up here, we had the purple well, the shallow wells. She's going to connect and mark the water levels in all the shallow wells, okay?
Okay, so let's see, shallow wells, not this one that's deep. So here we've got a shallow well,
right?
and here we've got a shallow well. But I think there's some water up here.
Is there a bubble?
Yeah, I've got a bubble in there.
Well, you could get the next one off.
I'll get the, okay.
I'll
Here's
fix it.
another one, and another. That's deep. Oh, really, there we go, much better. Okay, that's deep, and shallow, and shallow.
So if you connected those dots,
If I connect the dots, now this one needs to still settle in, so I'm gonna
all
skip
right,
it for the
just
moment.
skip that one, just skip that one.
In connecting the dots, hey, it has a downward slope. What should I do? Should I bring it down to the lake level?
Yes, because that's probably where it's connected, because there's no water up here, but there's that water, but that's different.
Okay, and then it goes all the way down to the lower
Right.
exit, correct?
Right, so we can sort of see that the water levels in a well are commensurate, draw a line between the left and the right, and that is, that's sort of a hydraulic gradient. It's driving water through the system. And since we know that, and if we, normally we don't have this perspective on what the groundwater systems look like. All we have is the wells and the depths to water. So if we wanted to drill a new well right here, we might anticipate the water to be where the line is because we've done all this interrogation. Now she's going to go along and draw the water levels in the deep wells.
With the green pen. So, oh, they're much higher.
They're higher. Yeah, that's very interesting, okay?
Where'd that one go?
And just sort of draw them. And you can sort of see the water levels in the deep wells are higher.
Oh, and should I draw this one for the?
Yeah, and we
pipette
actually
tip?
have this pipette tip. So draw the water level as though there was a water level there. So you can sort of see that the water levels in the deep well follow sort of a different surface, and because the water level rises up. And what you really see is the water wants to go down here, wants to go into the clay layer. It's not connected to this. The only way for it to go out is to rise up here. So again, it wants to seek an equilibrium, and it sort of has an equilibrium because there's a little water meniscus there that I think you can see. Now I think if Aaron is able to pull that out, before you do it,
Zoom
I
in.
want you to keep your eyes on the water that will be coming out of that well when the pipette is not there. It'll be flowing all by itself. So it's very subtle. See if you can see it.
Oh, there
Right,
it
so you
goes.
see the water coming out? If
And
you
then
put
if
it
I
back
put it back
in,
in, it fills right back up.
it fills right back up. Okay, so that's actually how a spring works. It flows all by itself, just like I demonstrated with the tube. And so a spring can be a natural formation, or a spring can be, or we can actually drill a well and it will flow all by itself. And I think what we're going to do now is just do a quick drought exercise. We're going to turn the water off.
Aha, no more water.
No more water. And I think,
But we still need to take water out of the system.
yeah, so, we still, even though it's not raining, we still have our needs for water. So we're going to be pumping the water. Okay, so let's pump some water.
Let's pump.
And it might take a while for her to do this. You might want to pump the city well. That'll take more. That'll take more out per unit energy, I think.
Takes so much energy to pump this.
Well, now you're going to get all this contamination coming out too.
That's what I was trying
We're
to
going to talk about that. So remember that picture when you get back to it, okay?
What's going to happen to the lake level while I'm doing this?
I don't know. I would imagine since there's nothing going into the system and you're pulling water out, that the water levels are going to go down. Just like if I were to drink my water and empty it out because nothing's going in. Normally when you drink a glass of water, you don't have water going in at the same time.
I hope there aren't any
But
fish
this is-
swimming.
Yeah, okay, well that's not too good. So actually we can see right now that the water level is now down to here. Okay, so the net effect of a lot of pumping is to reduce the water levels. And or when combined with lack of rainfall input, the water levels go down, okay?
Haha,
Now,
it's
the lake
dry.
is almost dry, and I think I've made the point, okay? So I think our next step is to reestablish our,
Here comes the spring rainstorm.
yeah, thank goodness. That's what we need. Okay. To summarize, what we saw is that, you can get water well pumping can do a lot of things. It can give you fluctuations between one well and another. If you're competing for water, it can dry wells up. Over large areas and over a long time, you can reduce the stored water, the water stored in the groundwater, so the volume of water stored goes down. You can dry up a lot of areas. You could potentially dry up lakes and shallow water bodies or wetlands. There's other impacts such as ecological or what we call subsidence issues, and subsidence is a situation where you remove a lot of water from a normally saturated rock or sands or gravels, And without that water in there, the weight of the geologic material will want it to settle and compact. And what that means is the surface elevations of the ground can go down. That's called subsidence. That happens in a lot of spots, and there's also these ideas of ecological impacts. I'll have a picture of that in a second. So one thing I want to do is, normally when I've done this, I bring up Google Earth and I do all these tours, but I think I want to take you to a couple of places and show you some pictures where some of these things are in play. And the first place I want to go to is Africa, and I want to go to the country called Libya. And I want to focus our attention in the blue box. And that's all I'm going to show you here, but I will say there in Libya, they have the so-called Nubian sandstone aquifer. Now, Libya is a country that's a little bit more wet than, say, Saudi Arabia, but most of the water in Libya, 95%, is not from seawater desalination, it's from groundwater. And you might ask yourself, well, where's all that groundwater come from if most of this country is in the Sahara Desert? And I'll tell you, it's coming from the Sahara Desert. And you say, well, why is that? And it's because there is a large aquifer underneath there that was filled with water thousands of years ago. And the climate has since changed. It was an aquifer back when the Sahara Desert wasn't a desert. And so the water stayed, and nobody pumped it out until now. You can bring this over. If you go to Libya now, you can actually buy this water, at least when I was there. And this, what they do is they produce this water, this ancient water. It's been dated to be, in some places, over 1 million years old. So it was 1 million years ago when that water entered or recharged that aquifer. It's been sitting down there ever since. And now what they're doing in Libya is 75% of their water is being pumped out of these aquifers in the south, and they're piped to the northern cities where all the population is, in this case, say, Tripoli. They have a large network of 4-meter diameter pipes, and they move the water up, and they're essentially mining the water because it's not getting recharged or replenished. So when I was there, the obvious question is, well, how long is that going to last? And I never got the same answer twice. So honestly, I don't know, but it's been working so far. They only have 6 million people in Libya, but that's kind of interesting. Now, I had some pictures of this, but I want to take you over to the green area. The green area is an area where this same kind of aquifers exist, and we're going to zoom in close in. There are lakes. So in the same sense, I have a lake here. There are lakes out in the Sahara Desert, and you say, well, where does that water come from? And that water comes from that aquifer. It's just collinear with the aquifer because there's no rainfall in the Sahara Desert that's appreciable. So that's it. And what does that look like? It looks like that. So there's an oasis. So if you're traveling over you read all these stories, Lawrence of Arabia over in Saudi Arabia or over here in the Sahara Desert, here is an oasis where the groundwater appears above the ground surface. You have all the plants, you have birds, you have lots of bugs, you have a whole ecology out here, okay? So I'm going to go to a different place now. So the different place is Jordan. This is in the Middle East. Now Jordan gets all their water from groundwater too, although there's a lot more precipitation in Jordan in general, but it's still a dry climate. And I'm going to focus in on the red box, okay? The red box, and now we got close in again. The biggest city in Jordan, the capital, is Amman. Amman has been growing tremendously over the past decades, and they have built water pipelines and wells further and further from the city. One of the places they focused on is the area in the red, which is an area where there was an oasis called the Azraq Oasis. And it was an area where the water actually bubbled up above the ground surface because the terrain was lower there. It's the bottom of a kind of a basin, and the water would collect there. But it was the same kind of thing as Libya. But the problem is now it looks like this because all the water has been drained. So you saw me pumping the water out over here, and the water levels went down. That's what happened here at this oasis. So what was living there and all the life that was there, a lot of it is now gone. And you can sort of see this is the way it was in 1998. All the water's drained. And the palm trees are hanging on for dear life, but it's not coming back, okay? So I have another picture. I'm going to switch gears, a couple of pictures. I mentioned subsidence. You pull all this water out, and the ground goes down, okay? And you say, well, how significant is that? Well, I think the most dramatic picture of this effect is shown here in the San Joaquin Valley, where the man is standing next to a large pole in 1977. You can see where the ground layer is. but in 1925, the ground layer was at the top of the picture. So the ground was a lot higher then, and it has gone down. That's one of the most dramatic. Usually you're looking at, maybe a couple of feet over tens of years, that sort of thing when you see it. But we can actually see it a lot better now because we can utilize satellite techniques. It's called the INSAR satellites. And basically it's a radar kind of based remote sensing technique where you can actually measure the ground elevation from a pass of the satellites in 1 year and come by 3 years later and measure the ground surface elevation later, and you can measure changes in the elevation millimeters or more, okay? And so people have done this a lot of places, a lot of cities in the Southwest. You can see a lot of very subtle subsidence going on. So this is kind of interesting. The next slide is going to show you something which is not subsidence, but it's another satellite technique used to try to estimate from a remote point of view at a satellite level how much groundwater has been extracted from a large area. So you might think to yourself, well, if I can measure the groundwater levels and visualize it the way I've done here, I can see how the groundwater is going down, and I can see how the water's been pulled out of storage. Some places you may not have all that information. Sometimes it's hard to get all the data. So NASA has a satellite called the GRACE satellite, and GRACE is a satellite that measures gravity, gravitational attraction. And so what they do is the satellite passes over a region a couple of different times, in this case 6 years apart, and they can actually measure differences of gravity. And a professor down at UC Irvine has utilized this information and to attribute that gravitational change to the loss of water pulled out of the ground over that period. So you can sort of see that in India, a lot of people have built a lot of wells, they pulled a lot of water out, no one's been keeping track of it, and no one really has an idea of what the net impact was until you look at it from this perspective, okay? So I think this is really kind of interesting that you can actually see groundwater from satellites when you don't have the data on the ground, okay? And they've done this in California as well. So I'm going to switch gears a little bit. What's my timing here? So I want to talk a little bit about groundwater quality. We've talked about how groundwater occurs, how it comes from rain, how we put it in the ground, how it comes out. But the other aspect about groundwater is it has a lot of constituents in it. A lot of times people, you drink mineral water. You look at the side of this, and it has a notation of bicarbonate and all sorts of minerals that are inside of this water that have been measured. And a lot of these minerals occur because of the geology. These things are soluble and they get into the water. And those are, if they're natural, I think of them as impurities. I use that word. They can include minerals, calcium, chloride, all these sorts of things. Some of them can be poisonous if they're concentrated enough, like selenium, arsenic. These are things that happen in California water, but they're never really high enough to be an issue. But you can keep an eye on them. And then you'll also find atmospheric gases. If you have fish, have to have oxygen, and they survive on oxygen that's dissolved in the water. So there's atmosphere exchanges, it's gases with the water, and there's certain solubilities of water. You can also find salt. So a lot of times if you have a groundwater basin near the ocean, underneath the ocean floor, if you went down, you'd find salt water. In most cases. There's actually an exception to that, but there's salt water down there. And so if you go over to the land side and drill a well down, you'll find fresh water. So if you connect a line between those two wells, somewhere in there is going to be some shift from salinity to fresh water. And if you pump the well on the land side to get all the fresh water, at some point you might suck in all that salt water, just as Aaron did with the red water here, okay? So then you can pollute the well with seawater. It's called seawater intrusion. Okay, so groundwater pollution is more the kind of things that we as a human species have dumped chemicals and had practices on the land surface that have led to pollution of the groundwater. These things could be from agriculture, from irrigation, from industries, big and small. They can be from urban runoff. You have a lot of rainfall in cities. You got all this stuff running off into creeks. And a lot of stuff might find its way into groundwater. You could have wastewater from sewage treatment plants or bad septic systems. All of these things, and of course the seawater intrusions, all of these things conspire to add some kind of pollution to the groundwater. This particular picture was I was on a project where we were trying to work with people in Kazakhstan in Central Asia, and they have a very important metallurgical facility there that does a lot of really important work with uranium and beryllium products, one of the biggest suppliers of beryllium in the world. Yet it's an industry and they have a waste stream, and this waste stream, as you can see, some of it's dumped into this pond here. And the question that they had was, they didn't have a lot of experience with groundwater pollution. And the question was, yeah, we think we've got this pond lined and there's clay underneath it, but we also think it's leaking and it's getting into the aquifer. And we want to work with you to figure out how it works. And so we ended up working with them on this. And so that's what that picture is from. So we're going to show you again back to the device here, the ant farm, if you will. We're going to pollute it up some more and show you some ideas of how pollution gets underground. One way is, I call it deep well injection. I think she showed you some, she's going to do it again. We started out by pumping some red dye down one of these wells. And you can think of that as that dye may be a contaminant or something. Somebody wanted to get rid of something and they dumped it in deep wells. Do you think anybody would be smart enough to keep doing that? I don't know. But that is a way that people have done it. They've gotten rid of stuff. They think they think it's going to be isolated from the shallow regime or isolated from some other places where they're producing water. A lot of times people don't understand how these systems communicate, how what I do over here affects what happens over here. Pump and treat is actually cleaning the water out. So you saw Aaron pulling water out of the system, all the red water. People have this idea, if I just keep pumping all this water out, I can get it all out of there. And that's a great expense. We have a landfill disposal. So there's also the landfill here, and she's dumped some stuff in the landfill. We're going to see what happens to that. And there's also a lot of chemistry. I won't talk a lot about this. I have one little thing I'll show you, but it's not just, colored dyes moving through groundwater. There's lots of chemistry that can occur. There's also lots of different kinds of fluids. You can have gasolines and products that don't mix well with water, and they form little bubbles, and they float, and they exchange liquids, and it's all very kind of a complicated thing. So it can go on and on and on. We'll just show you how some of this works. I think we're going to go to the model. So let's walk over here.
Why don't you give me your water and I'll put it back away?
No, I'm saving this. Okay.
Don't want to lose that. It's precious. Shall I re-inject?
Yeah,
Rid of lots of waste?
Well, first of all, she's going to re-inject here, but one of the things before you do it, you got blue in
Oh,
there?
wow, where'd the blue come from?
No, you don't want that.
No, I don't want that.
But one thing I will point out is she actually dumped some stuff in here at the beginning, and you saw it moving through here, okay? And you saw how this well is polluted, okay? And you saw here how she's put some stuff in a landfill, and maybe I should use this, and how it's actually moving right along the top, right along the top here, and it's going to move its way into the lake. Is it actually coming in there now? Here.
Yep, starting to come
Yeah,
in.
so it's actually coming into the lake. So she did that. And she did this before. You can sort of see there was a leftover of stuff in a well here, and it's just been bleeding out. Now she's doing another disposal of this chemical here, okay?
I don't want to pay to get rid of it. I'm just going to shove it down.
Yeah, it's midnight. It's midnight. But now the city well, we got to turn the city well back on, as we did this before.
Yeah, I'll dump it over there. It's far enough away from my house. Now I'm going to take a shower.
Okay.
Uh-oh, not good.
So that's not too good, okay? So that's how we discover these problems half the time, is a well becomes polluted. And all we know is that this well is polluted. We don't know what's going on at this well right next door. What if we pump the water next door?
Let's see what happens.
What happens here? This one right here.
Let's move the tip.
You can see what's going to happen, but normally you won't know, okay?
I think it's deep enough.
Right?
Ooh, nice and clean.
All right, so it's clean. So we're getting red out of this one, and we know that there's this landfill over here. Do you think we would assume that this red here is coming from this landfill? I don't know. I mean, you can tell right now that this red is coming from over here, and that was secret. The landfill is polluting this. So there's two different sources, and the real question is how do you figure out what's going on? Okay, so it's a tricky business, but this shows you pretty obviously how well things work. What you can also see is there's a little bit of red here left over from the show at 9:30 this morning, so it does take a while to get some of this stuff out. If she were to try to eliminate and pump this well We might want to see, can we get rid of it all? You know, this is, sometimes at the lab they have a large contamination problem because it used to be naval-based. They used a lot of solvents. Solvents are readily evaporate. You might think, if I just dump something on the ground, it's going to evaporate and go away into the atmosphere. But a lot of times it will get into the underground and will stay there and it will mix with the water. And you know, you worry about concentrations in parts per billion on some of these things in terms of their health impacts. So you're getting a lot of it out of there, but it's still here. It's not having any impact here. But what happens in doing this is there's a volume of water in storage that is no longer available for public use. So people worry and you try to protect it. Okay, and really what we have learned is try not to let it happen in the first place. There's a saying that's been very popular, you know, and a consultant crowd gets a chuckle once in a while, that the solution to pollution is dilution. And in some sense, there's some sense to that. Sometimes people want to address these problems by just letting them go and they become dilute, because you can sort of see the things become spread out and they become dilute. Well, there's another statement that's been made, and it was made in error, but I think it has some truth to it, or some reality or interpretation, which is the solution to pollution is delusion. So maybe if I kind of steer somebody's inquiry the wrong way, or I don't let them figure it all out, I can save myself. Well, I think really the approach is that the solution to pollution, if you will, is to really understand how things are working, like we're trying to show you here, understand the causes, the impacts, how the system behaves, you know, if you will, the fluid mechanics of the subsurface. And so, and to use that to not let it happen in the first place. And essentially a lot of that's happening, because what you see is there's a lot of rules, there's EPA, there's water quality regulations, there's, you know, it's very complicated with red tape, but it's all designed to try to not let this happen. Now, we can go up into hazardous waste disposal areas, there's proper ways to deal with things, and in the past there weren't. So the next thing I want to show you is, we don't have time for all these videos, or all these kind of demos. I'm going to show you some high-speed pictures, your time-lapse pictures, of a couple of situations like I've just shown you here. And in this particular case, there's a landfill you can see that has some red in it, and actually put a blue in that deeper shallow well there. And we can see what happens as they go along, okay? And you can sort of see how the red is moving in to the lake, and the blue is moving not as quickly for some reason, but it's moving to the right. And so we started to see the red going to the lake here as well, okay? So the next one I want to show you is a situation where we have the red there, and this is very much similar to what Aaron had already started to show you, but you can sort of see as a lake, it's going to eventually want to go to the right, and it's going to empty itself out in the right-hand side reservoir. Now, I'm going to show you the exact same thing again, except in this case, I'm going to operate the lake as a river. So really what I'm going to do is I'm going to operate a drainage behind it. Water will drain out of the river. So there'll be two ways water can leave the system: through the river, or can leave groundwater, through the river or the right-hand side reservoir. So in this case, that same injection is in fact going to find its way into the river and leave that way. So in this case, you can sort of see how the water will communicate with the surface water. I can get a pollution in the river that's coming from a groundwater pollution somewhere else, or vice versa. It can work the other way as well. The next thing I want to do is, I think Aaron's got a beaker of some red there.
Yep, right here.
We're going to talk about a situation where you have, say, two kinds of contaminants. A lot of times you have many contaminants. Okay, she's going to put some blue in the red. And
what do red and blue make?
Purple, all right. So my question that I want Erin to do is I want her to take that beaker home with her tonight and come back.
Gee, exciting.
Yeah, I want you to come back tomorrow, and you guys can come and see. I want her to split that water into two sub-volumes. Half the water in this beaker, half the water in another beaker. But I want beaker 1 to only be red, and I want beaker 2 to only be blue. Now, do you think she'll figure out how to do that? I don't know.
I think I could do some chromatography at home.
Chromatography. Okay. Now you got to use the same water. You can't fake it and recreate it. So the interesting thing is what I'm going to do is I'm going to put a time-lapse picture here, if you will, of the red and blue mixture into the well, one of these, to that well, and we're going to watch what happens, okay? So it's a little more dilute, so keep your eye on it. But I think what you can see is that the red and the blue separate out. The red moves faster than the blue. So how does that work? Because it's just riding on the piggyback of the groundwater, and that just goes at a certain rate. Why does one go faster than the other? I'm going to show that again, I think. Nope. So right there, the big well is pumping red, and then it's pumping blue, and then it's clean, or still blue. Okay, well, we're going to go back and look at that again. I'm going to one more time. Okay, now, keep an eye on the pumping well, the big one that she's always pumping, the big thick one. If I'm pumping water out of it right now, it's fresh water, okay? And if I'm pumping now, it's red. Now I'm going to get blue. So in time, if I have a time, I'm looking at a time, it's fresh, then it's red, then it's blue. How do I make sense of this? If I'm a guy at the lab working at the Water Supply Authority, how do I interpret that? And so what's really going on here is the blue is reactive. And the mixture of red and blue, what it does is at the molecular level, the blue molecules want to stick to the sand molecules, but not all of it. So there's, some of it wants to be, they want blue and water, there's an equilibrium. So, but the net effect of this is the blue is going to move slower than the water because it's hung up with all this reaction. And so the guy at the lab, when he takes samples of this, and if he doesn't have a water quality laboratory himself, at the water agency, if you will, they'll send it to a laboratory. They'll probably use a device that has the word chromatograph in it. And they'll, in fact, sample or run the water through a system that forces it to actually come out at different points at different times. And that's how they can tell different chemicals have different behaviors. So that's how that works. What's the next one? Okay, I'm going to shift gears a little bit here. And I'm going to go do a couple of examples, talk a little bit about some other areas. I'm going to focus here on the Imperial Valley in California, tell you a little story about the Imperial Valley is in that blue box down there, down by the Salton Sea, if anybody's been there. It's inland from San Diego. You can see the Salton Sea above there. One thing you notice here is that in the middle of the desert, there's a lot of agriculture, and the agriculture is big business, especially in the winter. A lot of things come out of there for the East Coast and much of the country because it's the only place where they can grow stuff in the winter. And the water for all that agriculture is imported from the Colorado River. This is what I talked about in the beginning. And there's a canal that runs from the Colorado River to the Imperial Valley. Originally when it was built, it was a ditch. It was an unlined ditch and a lot of water. And guess what? They lost a lot of water to the subsurface. So here's the All-American Canal. And they didn't like all this because they were losing all this water that was intended for the agriculture in the Imperial Valley. And what happened is it kind of built up a little mound on the groundwater, and people down south of that yellow line started putting wells in and growing, starting their own agriculture there off this groundwater that was accruing. Now the interesting part of the story is that yellow line is the Mexican border. So the people on the Mexico side were taking advantage of this water. This got people all very upset, So they ended up, in this picture you can sort of see there's two canals because one, they're rebuilding it. They rebuilt it now, it's all done. And they've lined it, so there's no more water loss from the well. So they didn't want to have any water loss from the well to the subsurface. They wanted it all to go to the beneficial use. That's the buzzword for the irrigation. So now we're going to shift gears, okay? We're going to contrast that situation with what's going on in Orange County. Orange County is a big part of Southern California, and in that yellow box, they might have between 2 and 3 million people living. And they get water from all over the place, but one of the places they get a lot of water from is their groundwater system. And one of the things they do with that groundwater system is they artificially put water underground. So what you can see here is a whole bunch of infiltration basins where water from various sources, and I'll explain one of them, they put it underground on purpose. So in contrast to what's going on in the Imperial Valley, they want the water to go into underground, and they want to store it in the groundwater basin. And one of the sources for the water that goes into these pits. So is in fact, it comes from the Orange County Sanitation District, which is in Fountain Valley. And really what goes on there is they got one of the most advanced water treatment systems in the world. And they pump a lot of that water back up, and it gets put into the ground in those basins, okay? So what you have is water gets used, it gets treated, it's put back into the groundwater reservoir, it gets used, it gets treated, and it's going round and round. So it's a nice recycling and reuse. And what that means is the amount of water that they take from here will satisfy the needs of 400,000 to 500,000 people, just from this. And that's a water they don't have to import from snowpacks that don't exist and reservoirs that are dry. So it kind of gets them off that old school grid a little bit. And so this is actually a new way of thinking about how to manage groundwater, okay? They say, well, is it only in Southern California? Well, a lot of it is. A lot of the very forward-thinking ways of doing this have started down there, but let's come to Livermore. I said that a lot of our water comes here in Livermore from the Delta, okay? And we talked about the South Bay Aqueduct. And what they do in years when they have water in the South Bay Aqueduct and they buy water and they can get extra water is they take some of it and they drop it into the Arroyo Mocho, and that will take it downtown between Livermore and Pleasanton. And you can see another set of these kinds of basins that are here. These are the old gravel pits down there. And Shadow Cliffs is there in the south. It looks like a kind of a triangle. That's the park. But they put water underground here too, in addition to what the normal rainfall gives you, okay? So this year, for example, they're getting very little contributions to the water here from the Delta, if any at all, okay? And what we're surviving on is groundwater. And so what we're surviving on in large part is water. A lot of that is what we put down there in the good years, okay? So we're actually using the groundwater as a reservoir, okay? So they're not recycling it the way you've done in Southern California. Once this groundwater is used, some of it will end up in this particular treatment plant. There's one in Pleasanton and there's one in Livermore, but this particular one in Pleasanton will treat water, and what they do with some of that treated water is they pipe it up into San Ramon and to Danville and to Dublin to water golf courses and schoolyards. Okay, so it's reused. It's not necessarily recycled because it doesn't ever come back into the system, but they're reusing it and they're making the most out of it. And the Livermore Golf Course, for example, the same thing is going on there. They get water from the Livermore treatment facility. So this idea of recharging the groundwater and reusing water and recycling water, to me, is something we need to become more familiar with. I think it's a really important thing, and they've done a lot of this. Santa Clara now, I think, is building a very large facility for treating water in the same way. And so I guess I'm coming to the end, but I'm not on much. I got one slide after this, but it's I wanted just to review. We tried, at least I tried to explain, how we get our water in California, where it comes from. And I wanted to explain how groundwater works. It's in the news a lot these days, so hopefully you can sort of see how some of these things work here now. It's actually quite important. It's probably more important than people give it credit for, especially now here in Livermore, because we're living off a lot of it. There's a lot of threats to groundwater quality, dumping things in wells and all this stuff. And, it still kind of occurs, I think, in some cases. But I think we're much more aware of things. And, I think more people are aware of what they do before they do it, And the idea is, how can we better protect it and use it in the future? I hope we got some ideas of that. Now, the last slide I have is something I hadn't planned on here, but I saw it in the newspaper on February 1st. I thought, gosh, are we there yet? And here's a picture where they're talking about oil waste being pumped into the aquifers in the state and in the San Joaquin Valley. And I'm going, why would they ever want? This is almost nonsensical to me that this is even being talked about and people are still doing this kind of thing. But you need to keep thinking that, we need to keep abreast of this and be diligent about these things. Because people still worry about this stuff and it still happens. And the only thing I would say in closing is that I would say that, 50 years ago, this probably was occurring as well, but it never would have made page one. So there's a little bit of progress. Right? But this is only 3 weeks ago, okay? And so with that, I think it's time for Q&A. So thanks for your attention. How we doing? Yeah.